you can insert this highlighted shape, in other words, insert that vacuum into this copper, or you can insert it into the copper, which would work in our case. You would get like a circle in here of a different color where that would just be vacuum. You can add them, and that just basically combines the two shapes. You can intersect them. However, what we want to do here is we want to cut away this yellow copper of brick. We want to cut away this circle, and you'll know exactly what I mean when I press OK. So click cut away, and then press OK. So you can see exactly what I mean. It literally cuts away a circle. So now we have a air-filled circle in the middle of our screen right here. Okay, so now you have successfully modeled the structure, which was relatively simple because this is it's a symmetric structure. It's very simple. So now the next step, you can consider that part 1 of this tutorial. The next step is before we move on to the next step, it's always good to save this, just in case it freezes up on you. So go ahead and save it as a duck round hole screen if you want. Press save, and there you go. You can see the name up here, and it's called inductive round hole screen. Okay, so now the next part, after you've modeled it, step 2 is to set the simulation up to be simulated. So the first part you want to do here, before I do this, I want to demonstrate the value of having these parameters down here. Remember when we defined, I said don't just enter the number, define a variable? Well, this is the value behind it. Let's say you want to change the thickness without having to go back and re-specify it. Let's say you want it to be 20. In other words, you want this thickness to be much thicker. All you do is change it, you enter in 20 down here, and then whenever you modify variables, you press F7 on your keyboard, and you can see it changes the thickness in a blink of an eye. It's very useful, and it becomes even more useful when you start running parameter sweeps. That's where the primary use comes in. But leave it at 5 for right now. Okay, so now that that's been covered, let's move on to step 2, which is setting up the simulation. So the first step is to go and change the units. Now, in my research, we're primarily concerned with the terahertz region, which is infrared light, essentially. And we're also looking at visible light, but let's go with the terahertz region. So change the frequency to terahertz. And because terahertz, the wavelength, if you convert that frequency into wavelength, it will be on the order of microns. And if you want to see any action or any interaction between the wave in terahertz that is incident on your screen, your screen has to be on the dimensional order of the wavelength of your incoming EMF wave. So therefore it needs to be in microns. So don't worry about temperature or time. Go ahead and click OK. Okay. Alright, so now the next step is to set up the frequency range. And the frequency range is basically the range of frequencies which CST will simulate the incident electromagnetic wave that is incident on your metamaterial screen. So let's go with it's not that narrow, but let's go with 0.6 terahertz to 5 terahertz. Enter that and click OK. So now the next step is to set up the boundary conditions. So now you can see what I meant by screens, right? This 1 unit cell right here is going to be infinitely replicated in the X and Y directions over here, and it becomes an infinite screen essentially. So that's what we're building here. It's not just a single little square cell right here. It's really a whole bunch of these things put together to make one big metal screen. And these things are very small, but these things are on the order of microns. Okay, so let's get back to the point at hand, which is the boundary conditions. So for most of these simulations, you're going to be using the default unit cell in the X-min and the Y-min direction, and in the X-max and the Y-max direction. However, for the Z-min and Z-max direction, the wave that's where the wave is actually going to be incident on. The wave needs some room to propagate, and if you don't give it room, you might get some errors or inaccuracies in your results. So you need to change that to open add space. And you can see what that does. It basically gives your screen a little area. So the wave is coming in right here where this purple thing is, right? And it gives it more room to propagate before it gets to the screen. Alright, so that's that. So you set up these boundary conditions as so. Now, just to give you another feeling about the boundary conditions, I want to show you what the electrical tangential boundary condition means. Now you'll learn this in electromagnetic theory class if you're a EE or if you're a physicist, but basically setting your x-min electrical to E tangential, setting your x-min or any boundary to an electrical boundary in CST basically forces, at this location, with this little green thing, it forces all the electrical fields at this point, it forces their tangential components to be 0, which is basically the equivalent, the physical equivalent of putting a big huge PEC, P-E-C, at this location, infinitely thick. And a PEC, I don't even know if that's what they call it, but a perfectly electrical conductor, PEC, is basically a conductor that has a conductivity of infinity. And it's defined, you'll learn this if you study boundary conditions of PECs. Yeah, it's defined as having E tangential as 0. Alright, so we're finished with the boundary conditions. I've told you about the tangential field, what it means, and what you can use it. So set it back to unit cell, because that's what we're dealing with. Make sure all these guys are unit cell, and you have the open add space here and here. So now you're finished, click OK, and now you can see your model and sort of what's going on. Basically, the wave is going to be propagating from the input port, which in this case is going to be over here actually. I'll explain what these things mean in a minute. So it's going to come like this and propagate through. Some of it's going to reflect back, some of it's going to transmit. So that gives us to the ports. Whoops. So you have two ports basically. The Z-min port, which is in the negative Z direction, and the Z-max, which is at the positive, the maximized most Z location. And basically they're at the boundaries, the open boundaries that you just set up. Now, in all my simulations, I always make Z-min the input port, and I'll show you how to do that when we actually run this sucker. So just keep that in mind, that Z-min is the input port. Now another thing to realize with these mode ports is that you have to specify a certain amount of Fouquet modes. And to get to this window right here, you have to double click on this. Let me show you. You can double click, or you can go right click properties, and the number